Welcome to this coding walkthrough. Today, we'll be tackling the problem number 498, diagonal traverse. This problem challenges us to navigate a matrix diagonally while alternating directions. It's a great way to test your understanding of array manipulation and traversal patterns. Let's dive in and explore how to solve it step by step. In this problem, we are tasked with traversing a given MXN matrix in a diagonal order. The goal is to return an array that contains all the elements of the matrix, traversed in a specific diagonal pattern. Let's consider an example to understand what this means. For the input matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, we start from the top left corner and move in a zigzag diagonal pattern. The output for this example would be 1, 2, 4, 7, 5, 3, 6, 8, 9. This means we have to carefully alternate between moving diagonally upright and diagonally down left to cover all elements in the matrix in the required order. Now, let's break down the traversal process for the first example. We begin at the top left corner at position 0, 0, which has the value 1. From there, we move diagonally upright to position 0, 1, with the value 2. Next, we switch directions and move down left to position 1, 0, with the value 4, and then continue down left to position 2, 0, which holds the value 7. At this point, we switch directions again to move upright, visiting position 1, 1, with the value 5, followed by 0, 2, with the value 3. From there, we go down left, visiting positions 1, 2, and 2, 1, with values 6 and 8, respectively. Finally, we reach the bottom right corner at position 2, 2, which has the value 9. This completes the traversal for this matrix example. For the second example, we have a smaller 2x2 matrix, 1, 2, 3, 4. The output for this matrix is 1, 2, 3, 4. Let's understand the traversal order. Starting at position 0, 0, with the value 1, we move diagonally upright to position 0, 1, with the value 2. From there, we switch directions to move down left, visiting position 1, 0, with the value 3. Finally, we move to position 1, 1, with the value 4. This example demonstrates how the diagonal traversal applies to smaller matrices. For the third example, we have a matrix with just one element, 1. The output here is straightforward, as the matrix only contains the value 1. Since there are no additional rows or columns, the traversal simply involves returning the single element in the matrix, which results in 1. This scenario highlights how the problem handles the simplest case of a single element matrix. Finally, let's consider some important constraints and edge cases. The matrix dimensions m and n can range from 1 to 10⁻⁴, and the values within the matrix can range from -10⁻⁵ to 10⁻⁵. Edge cases to keep in mind include single row or single column matrices, such as 1, 2, 3, 4, or 1, 2, 3, 4. Additionally, we must account for very large matrices with dimensions close to the upper limit of 10⁻⁴. Other potential cases involve matrices with negative numbers or zeros, as well as matrices where all values are identical. Handling these scenarios robustly ensures the solution works for all valid inputs. When tackling the diagonal traverse problem, the main objective is to navigate through the matrix diagonally while alternating between upright and down left directions. One approach to achieve this is the brute force method. The intuition behind this method is to use the sum of the row and column indices, I plus j, to group elements belonging to the same diagonal. By traversing the matrix and grouping elements into these buckets, we can collect all the diagonals. For diagonals where the sum of I plus j is even, the direction is upright, so we reverse those diagonals to follow the problem's requirements. Finally, we flatten all the buckets into a single result array. While this approach is straightforward, it requires extra space to store the diagonals and also involves additional processing to reverse select diagonals. The time complexity is O(m*n), as we visit each element once, and the space complexity is O(m*n), due to the intermediate storage of diagonals. An alternative and more efficient method is the optimized in-place traversal approach. Here, instead of pre-computing and storing the diagonals, we directly navigate through the matrix while keeping track of the direction we are traveling. This is achieved by maintaining a direction flag, which toggles between upright and down left. Starting from the top left corner, we traverse diagonally in the current direction and handle boundary conditions as we encounter edges of the matrix. For example, if moving upright and we hit the top row, we proceed to the next column, or if we hit the last column, we move down. Similarly, when moving down left, hitting the left column means moving down, while hitting the bottom row means moving right. This approach allows us to traverse each element exactly once, making the time complexity O(m*n), and it requires no extra space beyond the output array, resulting in a space complexity of O(1). The chosen strategy for this problem is the optimized in-place traversal approach, as it is both efficient and elegant. The key insights that make this approach effective are rooted in understanding the matrix traversal patterns. Each diagonal is uniquely determined by its starting point on the edges of the matrix, and the traversal naturally alternates directions between upright and down left. By observing how boundary conditions influence movement, we can seamlessly handle transitions. For instance, moving upright from the top row leads to the next column, while moving down left from the left column leads to the next row. The alternation of directions is easily managed with a simple flag toggle. These insights eliminate the need for pre-computations or extra space, allowing us to traverse the matrix directly while adhering to the problem's requirements. When comparing the two approaches, there are clear trade-offs to consider. The brute force method is simpler to implement initially, as it relies on grouping elements into buckets based on the sum of their indices. However, it requires additional space to store these intermediate diagonals and extra processing to reverse specific ones. On the other hand, the optimized in-place traversal approach is slightly more complex to implement due to the need to carefully handle boundary conditions, but it is far more efficient in both time and space. Ultimately, the optimized in-place traversal approach was chosen because it minimizes resource usage while maintaining clarity and correctness. By solving the problem in a single pass through the matrix without additional storage, it provides the most streamlined and effective solution for diagonal traversal. The diagonal traverse problem requires us to traverse a 2D matrix in a very specific zigzag pattern. The traversal alternates between moving upright along one diagonal and down left along the next. Our goal is to output a single list containing all the elements in this order. To get started, we first need to understand the matrix dimensions. If the matrix is empty, meaning it has 0 rows or 0 columns, we can immediately return an empty list since there's nothing to traverse. Next, we initialize a few key variables. We need a result list to store the elements as we traverse the diagonals. Additionally, a direction flag will help us track whether we're currently moving upright or down left. A value of 1 indicates upright movement, while -1 indicates down left. Finally, we start our traversal from the top left corner of the matrix, so we set both the row and column indices to 0. Now that the initial setup is complete, we proceed to traverse all the elements in the matrix. Since the matrix contains m*n elements, where m is the number of rows and n is the number of columns, we will perform exactly m*n iterations. In each step, we append the current element at matrix row call to our result list. The key part of the traversal is how we handle diagonal movements. For an upright movement, we decrease the row index by 1 and increase the column index by 1. However, if this movement causes us to go out of bounds, either hitting the right boundary or the top boundary, we adjust. If we hit the right boundary, we move down to the start of the next diagonal by increasing the row by 2 and setting the column to the last valid index. If we hit the top boundary, we simply move down to the first row. Similarly, for a down-left movement, we increase the row index by 1 and decrease the column index by 1. Here too, we need to adjust for boundary conditions. If we hit the bottom boundary, we move to the start of the next diagonal by increasing the column by 2 and setting the row to the last valid index. If we hit the left boundary, we move to the first column. After each diagonal movement, we toggle the direction flag by multiplying it by -1, ensuring that the zigzag pattern is maintained. Once all the elements have been visited, we simply return the result list, which now contains the elements in the required diagonal order. A key insight that helps with this traversal is recognizing that the sum of the row and column indices, row plus col, uniquely identifies each diagonal. This means that all elements along the same diagonal share the same value for row plus col. Alternating the direction based on the flag ensures the zigzag pattern, while proper handling of boundaries prevents any out-of-bounds errors. It's also important to account for edge cases, such as single-row matrices, single-column matrices, or even an empty matrix, to ensure the solution works universally. From a data structures perspective, we use a dynamic list to store the traversal order, allowing us to efficiently append elements as we move through the matrix. The algorithm is highly efficient, with a time complexity of O(m*n), since we visit each element exactly once. The space complexity is O(1), as we use no additional data structures beyond the result list. This makes our solution both time and space efficient, even for larger matrices. This solution to the diagonal traverse problem follows a systematic approach to group and traverse the matrix diagonally. We start by checking if the input matrix is empty or its first row has no elements, in which case an empty list is returned. Next, we determine the dimensions of the matrix, m rows and n columns. We initialize an empty dictionary diagonals to group elements by diagonal levels, where the diagonal key is the sum of the row and column indices, I plus j. We iterate through each element of the matrix using nested loops. For each element at position I, j, we calculate its diagonal key as I plus j and append the element to the corresponding list in the diagonals dictionary. If the key does not exist yet, we first create an empty list for it. Once all elements are grouped by diagonals, we process them in sorted order of their keys. Diagonals with even keys are traversed in reverse, to produce an upright zigzag pattern, while diagonals with odd keys retain their original order, down-left zigzag pattern. The result list is constructed by extending it with elements from each diagonal, either reversed or as is depending on the parity of the key. Finally, the result list contains the elements in the required diagonal traversal order and is returned as the output. This approach ensures correctness and efficiency, with a time complexity of O(m*n), due to the single pass through the matrix and the processing of diagonals. Here, we start implementing the solution for the problem in Java. First, we import the necessary utilities such as java.util for working with lists and maps. Then, we define our solution class and the method findDiagonalOrder, which takes a 2D matrix as input and returns an array of integers. To handle edge cases, the code checks if the matrix is null, empty, or has no columns. If any of these conditions are true, an empty array is returned immediately. Next, we calculate the dimensions of the matrix, m and n, representing the number of rows and columns, respectively. We then declare a hash map to group elements by their diagonals, where the key is the sum of the row and column indices, and the value is a list of integers belonging to that diagonal. Using nested loops, we iterate through each cell of the matrix. For each element, we calculate its diagonal key as the sum of its row and column indices, ensure there's a list initialized for that key in the map, and add the element to the corresponding diagonal list. This effectively organizes all elements into their respective diagonals. Now, with the diagonals grouped, we proceed to construct the result array. We initialize an empty list called result to store the final order of elements. Using a for loop, we iterate through all diagonal keys from 0 to m plus n2, which represents the maximum possible diagonal index. For each diagonal, we retrieve its corresponding list of elements from the map. If the diagonal index is even, we reverse the list to ensure that elements are traversed in the correct order. Once processed, the elements of the diagonal are added to the result list. After iterating through all diagonals, we convert the result list to an integer array using a stream operation and return it. This completes the implementation, ensuring that all matrix elements are traversed in the desired diagonal order. To solve this problem, we'll start with a small 2x2 matrix as our example. First, we initialize some variables. The dimensions of the matrix are m equals 2 and n equals 2. We create an empty list result to store the final traversal order, and a dictionary called diagonals to group elements based on their diagonal indices, which are determined by the sum of their row and column indices, I plus j. Next, we iterate through each element of the matrix. For the element at I equals 0, j equals 0, the sum I plus j is 0, so we add 1 to diagonals, 0. At I equals 0, j equals 1, the sum is 1, so we add 2 to diagonals, 1. Similarly, for I equals 1, j equals 0, the sum is 1 again, so we add 3 to diagonals, 1. Finally, for I equals 1, j equals 1, the sum is 2, so we add 4 to diagonals, 2. By the end, the diagonals dictionary groups elements as 0, 1, 1, 2, 3, 2, 4. Now that we have grouped the elements by their diagonal indices, we process the diagonals in the order of their keys. For key k equals 0, the diagonal contains 1, which we reverse and append to the result list. Since it's a single element, the result becomes 1. For key k equals 1, the diagonal 2, 3 is kept as it is and added to the result, updating it to 1, 2, 3. Finally, for key k equals 2, the diagonal 4 is reversed and appended to the result, which doesn't change its order since it's a single element. The final result is 1, 2, 3, 4. This matches our expected output for the 2 by 2 matrix. Moving on, let's consider a rectangular matrix with dimensions 2 by 3. For the rectangular matrix example, we start with initialization. The matrix dimensions are m equals 2 and n equals 3, and we create an empty result list and an empty diagonals dictionary. Next, we group the elements by diagonal indices. For I equals 0, j equals 0, the sum I plus j is 0, so we add 1 to diagonals, 0. For I equals 0, j equals 1, the sum is 1, so we add 2 to diagonals, 1. For I equals 0, j equals 2, the sum is 2, so 3 is added to diagonals, 2. Moving to the next row, for I equals 1, j equals 0, the sum is 1, so 4 is added to diagonals, 1. For I equals 1, j equals 1, the sum is 2, so 5 is added to diagonals, 2. Finally, for I equals 1, j equals 2, the sum is 3, so 6 is added to diagonals, 3. By the end, the diagonals dictionary is 0, 1, 1, 2, 4, 2, 3, 5, 3, 6. Now, we process the diagonals in key order. For key k equals 0, the diagonal 1 is reversed and added to result, becoming 1. For key k equals 1, the diagonal 2, 4 is added as is, updating result to 1, 2, 4. For key k equals 2, the diagonal 3, 5 is reversed and added, making result equals 1, 2, 4, 5, 3. Finally, for key k equals 3, the diagonal 6 is added directly, yielding the final output 1, 2, 4, 5, 3, 6. In the case of a single row matrix, the process remains consistent. First, we initialize the variables. The matrix has dimensions m equals 1 and n equals 4. We create an empty result list and an empty diagonals dictionary. Then, we group the elements by their diagonal indices. For I equals 0, j equals 0, the sum I plus j is 0, so 1 is added to diagonals, 0. For I equals 0, j equals 1, the sum is 1, so 2 is added to diagonals, 1. For I equals 0, j equals 2, the sum is 2, so 3 is added to diagonals, 2. Finally, for I equals 0, j equals 3, the sum is 3, so 4 is added to diagonals, 3. At this point, diagonals contains 0, 1, 1, 2, 2, 3, 3, 4. Next, we process the diagonals in the order of their keys. For k equals 0, the diagonal 1 is reversed and added to the result, resulting in 1. For key k equals 1, the diagonal 2 is added directly to the result, making it 1, 2. For key k equals 2, the diagonal 3 is reversed and appended, updating the result to 1, 2, 3. Finally, for key k equals 3, the diagonal 4 is added as is, resulting in the final output 1, 2, 3, 4. This demonstrates how the algorithm works seamlessly for a single row matrix, adhering to the diagonal traversal logic. With this, we've covered examples for different matrix shapes and sizes, showing how the method adapts to each scenario while maintaining consistent diagonal traversal. To analyze the time complexity of our solution, we can break it into two main steps. First, we group the elements of the matrix by their diagonal indices. This involves iterating through every element in the matrix using a nested loop, one loop for the rows and another for the columns. For each element, we compute its diagonal key as the sum of its row and column indices and then append the element to the corresponding group in the dictionary. Since there are m*n elements in the matrix, this step takes m*n time. Next, we process these diagonals by sorting the keys of the dictionary, reversing the elements of even index diagonals as needed, and appending the results to our output list. Sorting the diagonal keys takes O, d asterisk log, d, where d is the number of diagonals, which is at most m plus n 1. However, since d is much smaller than m asterisk n, this sorting step is negligible compared to the time required for the grouping step. Finally, processing the diagonals involves iterating over all m asterisk n elements, which requires another O, m asterisk n, time. Thus, the dominant operation is the grouping step, resulting in an overall time complexity of O, m asterisk n. When we combine the time spent on grouping elements by diagonals and the time spent processing those diagonals, we get O, m asterisk n, for each step. This means the total time complexity for the entire algorithm is O, m asterisk n. Now, let's consider space complexity. The first contributor is the auxiliary space used by the diagonals dictionary. This dictionary groups all elements of the matrix by their diagonal keys, and since the total number of elements in the matrix is m asterisk n, the dictionary requires O, m asterisk n, space. The second contributor is the result list, which stores the final output. Since it contains all m asterisk n elements of the matrix, this also adds O, m asterisk n, to the space complexity. Both of these components are necessary for the algorithm to function and dominate the overall space requirements. An additional but minor contributor to the space complexity is the temporary space required for sorting the diagonal keys. Sorting involves space proportional to the number of keys, which is equal to the number of diagonals, or m plus n 1. This adds O, d, space, where d is much smaller than m asterisk n. As a result, this term is negligible when compared to the space required by the diagonals dictionary and the result list. When we sum up these components, the total space complexity becomes O, m asterisk n, dominated by the space needed to store the dictionary and the result list. Importantly, this space complexity remains consistent across the best, average, and worst cases. This consistency is due to the fact that the algorithm always processes all elements of the matrix and all diagonals, regardless of the specific input. Thus, the time and space complexities are O, m asterisk n in all scenarios. To put this into perspective, consider a brute force approach that iterates through the matrix multiple times, once for each diagonal. This would lead to a significantly higher time complexity of O, m plus n, asterisk m asterisk n in the worst case, as parts of the matrix would be revisited repeatedly. Our current approach optimizes this by grouping elements into diagonals in a single traversal of the matrix, achieving the more efficient time complexity of O, m asterisk n. In terms of space, the current solution is also optimal, as it only uses O, m asterisk n, space to store the intermediate diagonal groups in the final result, which is the minimum required to handle all elements of the matrix. Finally, we can validate the big O analysis mathematically. Each element of the matrix is visited exactly once during the grouping step, contributing O, 1, work per element, and with m asterisk n elements, this step is O, m asterisk n. Similarly, during the traversal step, each element is processed exactly once, contributing another O, m asterisk n. Sorting the diagonal keys adds O, d asterisk log, d, but with d equals m plus n 1 being much smaller than m asterisk n, its impact on the overall complexity is negligible. Combining these observations, we confirm that the time complexity is O, m asterisk n, while the space complexity is also O, m asterisk n, making this solution both efficient and optimal. One of the most common mistakes when tackling the diagonal traverse problem is overlooking edge cases, such as when the matrix has only a single row or a single column. These situations can lead to index out-of-bound errors if the traversal logic assumes that both dimensions are always present. Another frequent error involves the direction switching logic. For instance, when moving upright, crossing the top boundary means you should move right, but hitting the right boundary means you need to move down. Mismanaging these transitions can cause the traversal to fail. Additionally, some solutions rely on unnecessary nested loops to traverse diagonals, which increases complexity to O, n squared. A more efficient approach would use a single pass traversal. Lastly, some implementations waste extra space by storing diagonals in separate lists before merging them, even though the problem can be solved with O, 1, additional space, highlighting the importance of optimizing both time and space usage. Another common pitfall is failing to account for non-square matrices, where the number of rows and columns are unequal. Assuming a square matrix can lead to errors when indexing out of bounds. A useful insight for problems like diagonal traverse is that each diagonal corresponds to a constant sum of indices, I plus j. Recognizing this pattern can simplify your logic in both this problem and similar ones. From an interview perspective, it's critical to aim for an optimal solution with n time complexity and 1 additional space. Interviewers often expect candidates to avoid extra memory usage. Proper boundary handling is also key when moving upright. Transitioning at the top row means moving right, while hitting the last column means moving down. Similarly, for down-left movement, you go down if you're at the first column and right if you're at the bottom row. Lastly, if you're asked to discuss brute force approaches, acknowledge their inefficiency and highlight why the single-pass solution is superior. There are several related problems that share similar traversal patterns. For example, LeetCode 54 explores the spiral matrix problem, and LeetCode 59 builds on that with spiral matrix 2. Meanwhile, diagonal traverse 2, listed as LeetCode 1424, is a natural extension of this problem. When comparing approaches, the brute force method involves collecting each diagonal into separate lists, reversing them as needed, and then merging them. While straightforward to implement, this approach has a time complexity of n and a space complexity of n due to the storage of diagonals, making it less efficient. A more optimal method is direct simulation, where you traverse the matrix in alternating directions while dynamically managing edge cases. This approach achieves an n time complexity with 1 additional space, making it harder to implement but much more efficient overall. Another alternative approach is coordinate mapping. In this method, you use a hash map to group elements by the sum of their row and column indices, I plus j. Each group corresponds to a diagonal, which you can then process as needed. This approach has a time and space complexity of n, as you're storing the diagonals in the hash map. While it's not the most optimal solution for the diagonal traverse problem, it's particularly useful for extensions, such as diagonal traverse 2, where this grouping logic can simplify handling more complex input structures. However, for the original problem, the direct simulation method remains the most efficient choice in terms of both time and space. Great job on completing this problem. To recap, we explored how to traverse a matrix diagonally while alternating directions. We discussed its time and space complexities and highlighted the importance of breaking down the traversal logic. Keep practicing problems like this to sharpen your skills. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!